Good afternoon. This is Mike Newton, and I'm the director of Strategic Technology for two companies, Sciperio and Nscript. I also want to start out and thank the session chairs and for IMAPS National for putting the symposium together and allowing us opportunities to present. So what I planned on covering, first I want to apologize for not making it there in person, but I'm there in spirit for sure. What I'm going to cover is how 3D printed electronics of application-specific electronic packaging, and in the DoD instance, it could be mission-specific electronic packaging for chip-level integration. Go a little bit about Sciperio and Nscript and how they relate to each other. Sciperio is really a technology company, and I spend majority of my time here. But basically, Sciperio has been developing technology since back in 1999. And one of the early DARPA programs called the Mesoscale Integrated Circuit program was really looking at printing technologies for building electronics. And so from that technology that was developed, it actually emerged, and we commercialized that into a company called Nscript. So Sciperio is the parent company of Nscript. We still are the technology engine behind a lot of what comes out of Nscript. And what you'll see over the timeline, we've been really broad in a lot of the technologies that we support, including bioengineering, printed electronics, and mechatronics. Up until recent times, what you have is a bioreactor that we developed for the on-demand blood program, and then also developing 3D printed CubeSats for Space Force. And about Nscript, they're an OEM, so they basically have taken the technologies for microdispensing, integrating that with 3D printing, and developing what we call direct digital manufacturing. So it's a broad capability within what we call factory and a tool, technologies within a platform that you can build processes by virtue of the different heads that you do integrate into the system. And so so a lot of what's come out of that is what we call 3D printed electronics, and basically integrating structure with electronics. So a lot of people have been following the CHIPS program. We're no different than anyone else. We've been following closely, seeing where we play in this. So there has been a fair amount of funding put out there, particularly early on with DARPA and their version of CHIPS. And then as things emerge from Congress, the CHIPS program and the new initiatives that DARPA has also done for the Electronics Research Initiative 2.0. That's about $3 billion set to be spent over the next 5 years. And then, of course, the Navy's program that talks about chiplets and basically disaggregation of chips into functional level chips that can be built together using new substrate technologies. And so with that, as things progress in the advanced packaging realm, what we are seeing is some blurring of the edges of different processes, starting at the silicon level and then all the way up to the printed circuit board level. Some of the printed circuit board technologies, the high density interconnect technologies have supported and is supporting interposer substrates for packaging, multi-chip packaging. And then there's lithography that's being used for creating things like glass substrates, which Intel has been investing significant amount of resources in developing large scale substrates arrays that they do on glass. So with that, from a 3D printed electronics point of view, it's really all about integrating multiple processes. And with that, these processes can include the microdispensing, which is the ability to print conductive materials, dielectric materials, and viscosities ranging from 1 centipoise all the way up to 2 million centipoise, as well as doing other processes, not only additive, but also subtractive. Whether it's milling, we have lasers that can get integrated for doing micromachining, and various post processes for curing and sintering of materials. And the whole idea is what we call a factory in a tool, and being able to integrate these disparate type processes within the same platform that enable us to be able to do 3D printed electronics, and do that in a way that gives us some unique opportunities for chip level packaging. And also with 3D printed electronics, you'll see a theme going here is really integrating the multi-processes and developing the workflow that goes along with it. So we do have strategic relationships with people, with companies like Siemens, and looking at digital twin and workflow, and basically digital twinning the process, and then being able to take things from concept to physical parts is where we go with all of that. But again, it's about being able to integrate the various processes within the same platform. So the next thing is, once you have processes, but you also have materials. And so in building structural electronics, it really is looking at the various materials that are required for building structure and the various materials required to build electronics. And also then doing all the testing required to understand what you do to a structure when you add an electronic function. But again, it's about adding a lot of capability within the packaging, and being able to embed a lot of these things into the structure or into the substrate. And then, the ultimate goal is the green button. You hit the green button and then you start building parts. Part of that is you got to build into your system capability metrology so that you're able to monitor the parts that you are building, and then monitor things like volumetric flow, and various materials, temperatures, the environment that you're printing in, and so forth. So it's really looking at various modalities and being able to look at and test certain things, and being able to characterize your process not only in preparation for building, but also during and in situ when you're doing the manufacturing of your parts as you go along. And then really getting into the chip level packaging and looking at how you're able to embed these things, and then being able to do the interconnect, and also adding functionality for the chips, and being able to do interconnect not only in the X and Y, but also in the Z direction, but also looking at how you can do things from an integration point of view that allows you to do various size parts, and then parts that basically you get to move into a shape agnostic realm in the way you design these parts, and then the way you're able to place and do the interconnect. But again, it's really understanding the processes that are required, and also the disparate materials that you have to integrate, and then how you deal with different temperature regimes of curing materials and sintering materials and so forth. And then also understanding the interfaces that are involved with the various materials and the interfaces involved at the chip level. So again, being able to integrate multi-chip, it's really about looking at the capability of going beyond just a traditional package and even going beyond stacking too. So the ability to be able to run interconnect on any surface and any shaped surface is another capability that allows you to do some unique packaging opportunities depending on what your application may be. This is an example of a 300 micron stainless steel wire in which we are able to dispense dielectrics and also dispense interconnects, but also the laser that was integrated was able to do micro machining flat on the wire and then pick and place the chip onto the wire itself. The wire is a Kapton coated stainless steel wire, so you're able to place it. But then you also have the dielectric that's required to insulate the silver conductors that are needed for doing the interconnect from chip and then along the wire itself. And so what you're looking at is a 300 micron wire, but trace widths of, and we actually got down to 50 micron trace widths that run the length of the wire. And so this wire has basically a sensor that you can insert into the application and then be able to measure and take data remotely externally to the area that you're actually trying to measure. So with 3D printed electronics, you know, the capability is pretty vast in the sense that you're not limited to substrate types. You're able to use whatever substrate materials that you might have and what you design to, but then you also have the capability of actually making the substrate as you print your interconnect. So we typically call that printed circuit structures, PCS, kind of play on printed circuit boards. It's not what I would say a traditional printed circuit board because the design rules and the materials involved are very different. And so you have to design for it. So just transferring a PCB design to say a 3D printed electronics design has to encompass the ability to design for the technology in and of itself. Having said that, you still have a very similar digital workflow in that you can do the schematic, develop the electronics in the schematic and the like, and be able to export that and be able to fabricate and create different file types depending on the kind of technology that you're using, or whether you're moving into more of a true 3D. In the case here, this example is a cylinder in which the cylinder was printed, and we do cylindrical printing where you can be able to take the design and then it's transferred into a kind of a file form factor that gives you the machine capability to be able to print the various shapes and also be able to integrate the conductive materials and then also integrate chips depending on the levels and depending on where whether it's on the surface or embedded. The cylinder in the middle, bottom middle, actually gets fully embedded, so you wouldn't even see the electronics here. The one on the bottom left is a ABS, just a regular ABS thermoplastic that was 3D printed. And while it's printing, we have the micro dispense head that is also used to do the printing of the conductors, and then you just layer that way. So it has more of a look and feel of a printed circuit board, but again, different materials that you would use here. So you have to design for the thermoplastic depending on frequency that you need to do. And in the bottom right is actually ceramics. So we do print ceramic slurries, and we can print onto ceramic substrates. And so again, you have an opportunity to use different various materials. And of course, what we call flexible hybrid electronics, which are really the examples that you see across the top, being able to do those kind of applications, as well as there's opportunities to do things like textile, smart textiles, and so forth. But all of this is in using the 3D printed capability and being able to use 3D printed electronics in a variety of ways that allows you to go from different technology base. And so in this case, the design was split in such that in the earlier example, it's a fully printed board with the integrated microcontroller. This is an example where you fully 3D print the substrate, but then print a Kapton based interposer. And again, it's using the same microdispensing capability, the same what we call, again, factory in a tool to give you different type of substrate technologies and being able to integrate them in a 3D way. And then also one of the reasons, and a lot of our DoD customers are very interested in being able to integrate multiple functions. Again, if you think about size, weight, and power, size being able to become very volumetric in basically increasing your functional density. So you be very volumetrically and so forth. And so what you'll see here, again, some of them are cylinder based. Then the bottom right is an array, antenna array, and it's on a conformal surface. Again, the structure was 3D printed, and then the array itself is projected. So basically, you can do a design. We have the software where you project, and then be able to allow for any distortions, and then be able to print onto that conformal surface, and again give you a good functional capability. And again, the word I was trying to remember is volumetrically efficient is the thing. So so again, a lot of capability adding more function and functional density in chip level packaging starts becoming very very important, particularly with the DoD wanting to integrate and adding more, because a lot of times the volume they have never changes. They just need more function in the volume that they have. So particularly in some of the older DoD platforms out there. This is an example. This is a program we have with Space Force, and this enables us to take all of the processes that I have outlined earlier, and then a lot of the multiple materials, and then actually build systems. So not only talking about chip level packaging, but also building the whole system. You know, what we look at is like in the CubeSat. I mean, that's basically an electronic package. And it's very volumetrically challenged. So the whole idea is to be able to embed in the structure more function. Basically, what the satellite is required to orbit and do its traditional functions, and then allows you to add more payloads, because everything is now become embedded. So what this offers opportunities is to increase payload and then be able to add more functionality in a very small form factor. These are all 3D printed. What you'll see on the upper left is a heater. That was some test structures that we did. In the middle, you can see with a FLIR that we are taking measurements, and we can actually tune the heat. And all that data was taken and then moved into a more 3D. So what you have is a battery clamshell, so that the batteries are placed into the clamshell and the heaters are adjacent to the battery. So you get better heat transfer. So in space, when it gets very cold, you're able to maintain the temperatures of your batteries, and so that increases the life of the batteries and helps with the load. Also, what you'll see on the bottom left is we did more traditional substrates, all 3D printed. The bus that it gets plugged into is also 3D printed. And so these are early test pieces that are getting transferred into the satellite. Again, a lot of that gets embedded in the structure. And so again, this allows you a better functional density in the capability, and being able to, again, look at multi-material, multi-process, and multi-function. And so this is really what the 3D printed electronics capability can give you, and also allow you to, it really opens up a lot of design capability and opportunities to do things you couldn't do before, and then be able to apply them here. The detumbler, if you're familiar with satellites, when they deploy them, they tumble and then they settle out. But they use electromagnetic detumblers to stabilize them, to stop them tumbling. So we were able to fabricate a detumbler with embedded solid copper wire that enables that capability within this CubeSat. And then finally, integrating to multi-location. So, we have traditional brick and mortar. There's going to be a lot of decentralization of manufacturing a lot of times. DoD is very interested in that, so they don't have a single point failure in anything that they build. And then also being able to, we provided capability in austere environments. That includes the desert. And we've also developed a mobile capability that you can build out. It's an expandable Connex box shipping container. And then finally, we have our bio team developed a bioprinting capability that is now on the International Space Station. And it's last year, I think they were doing knee cartilage. We are developing a 3D printed electronic system that will launch in 2024, and that too will be on the ISS. Obviously, there's interest in manufacturing in space, manufacturing on the moon, and ultimately manufacturing in Mars. So you can think of these platforms becoming very autonomous systems, and being able to handle those with the files and plus understanding the cybersecurity aspects of all of that. And then finally, I'd like to thank, a lot of this work has been done by many people, and certainly the team that you see here is very much part of the CubeSat applications that we're doing. And so I definitely want to thank the team, because without them, I wouldn't be here presenting for sure. And so finally, so this is NScript. So if there's interest in that capability, certainly reach out to them. And then also, again, you'll find my email. Please email me any questions, comments, and so forth, and I'd be happy to respond to those. And so again, I apologize for not being there. Please enjoy the show. I plan on being there next time, and certainly will be at the device packaging. And so again, thank you for your time and your attention. And certainly recording is a challenge, because this is not my normal way of presenting, but here you are. So, but again, thank you for your time, and I'll see you in my travels. So thank you very much.